but she did that. Now, the simplest way of understanding how combinatorial group theory is used in cryptography is what's called a free group crypto system. Now, from the viewpoint of the people in here who studied combinatorial group theory, it's not surprising that it's used in cryptography. Why? If you think about it, combinatorial group theory is a crypto system. Because you have something called a group, which is a real thing. Then you have a presentation, and the presentation is a way of encrypting the elements in a group. So it really is a crypto system, combinatorial group theory, in and of itself. But let me explain how it's done in a real thing. This is called free group cryptography. Now you start out with a free group, and from the view, a free group is a group that has no relations. So you have a bunch of generators, and we're going to use this in our crypto system later on, so this is good. And every element has a unique expression as a word in these generators. Now how do you encrypt things? Well, what you do is the simplest thing is, suppose that you have some alphabet, like the English alphabet, A, B, C. Now in ASCII, I think you need 256 symbols to do everything. So you choose 256 symbols to do stuff, and you associate each one of the 256 symbols with a word in the free group. Okay, so what we have is, instead of A, B, C, I have W1, W2, W3 up to W256. Now, suppose you have a word in the plain text alphabet, like make love, not war, something like that. Okay? So, what you do is, you just replace the letters by the corresponding free group words. You make it a word in the free group, you send it out. Now, in a certain sense, though, you can't just send out the word, because that's just a word in a bunch of letters, and an attacker could say, oh, this is this, and just read it. So you need some concrete representation different than the word. And that's the idea of a homomorphic crypto system. So maybe instead of sending out a word in the generators, you send out a matrix representation of the word. You send out matrices. Now, how do you recover the word? Well, it turns out there are standard algorithms for rewriting words in a free group. Some of these you may have come across, Reidemeister, Schreier, Starlings, Foldings, whatever. So what happens is, you get the word, and now you rewrite it in terms of the W's, and you can get the message back. That's the basic idea of free group cryptography. One of the earliest. Now we tend to think of group-based cryptography as, say, starting with what I said, Wagner, Magyar, or Angelo Goldfeld. One of the things in looking this over, and we mentioned this in a paper, that in the late, I think it was in the early 70s, Magnus had who's the seminar's name for Magnus this afternoon, was studying the modular group. I said I wasn't going to talk about old stuff here, but I'll, this is modular. He had the modular group. Now what is the modular group? The modular group is all the matrices AD minus BC equals 1, where A, B, C, and D are integers. That's called the modular group. And in essence, I say this in almost all my talks, but that's the single most studied finitely presented group. If you count the number of papers, I mean, it's a tremendous number of papers, because it comes up in complex analysis, comes up in number theory, and comes up in group theory. But when Magnus was studying it, and what he came up with was the following theorem. And it's the first mention that I found of group-based cryptography. He proved the following theorem, that if you look at these matrices, plus, minus, and those things, where T varies from 1, 2, 3, and so on, they freely generate a free subgroup. So those are generators of the subgroup. Now what Magnus suggested, now this is before all this group-based cryptography in the early 70s, is choose enough of these to encrypt. In his theorem, the first column completely describes the word. That there's a one-to-one correspondence between the first columns of these matrices and free group words. So if you know the first column, you know the free group word. So what he suggested was exactly what I said earlier, is choose a bunch of things, do that, you look at the first columns, and that gives you an encryption, which is unique. Now, he does this early 70s, it doesn't carry it out, it's just a random thing in a paper. But it turns out there's evidence, I don't know what the evidence is, although they wrote a paper. Mike Anschel, who was Anschel Goldfeld, wrote a paper where he goes through some old stuff, and he believes that Magnus and Philip Hall were involved in cryptography in World War II. And he has some interesting things there, like why would you believe that, and so on. But he knew about this group-based cryptography before it started to become fashionable. What's interesting, and we've tried to do something with this. I want to go the other way. No, I want to go this way. You see this? If that t is a variable, okay, let's say you're in a polynomial ring now, and you consider those matrices over a polynomial ring, they still generate a free group. So what you can do is you can encrypt in here, and then your secret key is the value of t in the modular group. And we've been trying to work out some ways of doing that in terms of encryption. Gabriel, for your benefit, let me go back 3 slides.
Polynomial ring in one variable?
There, see? There you are. So, just give him his... Now, I just mentioned that. Now, unfortunately, pure free group crypto systems are very easy to break. Now, essentially what you do, you want to figure it out, use what's called a length-based attack. Free groups have a certain length, you chop off, and there are a lot of ways to break free group crypto systems. However, there was an attempt, we did it, myself and Gilbert Baumslag and Xiaowei Zhu, who was a student of both me and Baumslag. We found a way to do a free group crypto system over the modular group. And it actually works. It has some problems, but it actually works. And it can be used. So it's not completely worthless, but free group crypto systems can be broken. However, what we want to go to now is one application of cryptography, which is cryptographic authentication. Now, if we take a look, authentication refers to the process of determining whether an encoded message, you're not trying to find out what's in the message, you're just trying to find out, does that message come from who is saying it's coming from? So let's say you're a bank, and you get a message from a user, and the user says, deposit $50,000 in so-and-so's bank account. Well, for the protection of your customers, you need to know, is that really coming from that person? Now, there are many kinds of cryptographic, it's also, you want to make certain, and we get this all the time, is who's sending us stuff authenticated? You've gotten all these things. I am General Obi-Wan Kenobi of the Nigerian police. Please give me your bank account number and you'll get $1 million in your account. Has everybody got that? I've done it 5 times. I haven't gotten $1 million. Actually, they're all scams, but sometimes you get from banks. It says, and this is another scam. They say, we are having trouble with your account. Please send us, and it looks legitimate. How do you know? How do you verify? Now, so there are many authentication protocols that do this type of thing. Zero-knowledge proof. Now, zero-knowledge proof is essentially a proof that something is true without actually proving it. We won't get through that, or that you know a proof, even though you don't prove it. Digital signatures. Now, in the basic course, you talk about hash functions and using a hash function as a digital signature. Then there are challenge response methods. And it's this third one that I want to do with a combinatorial group theory, and I'll explain what it is in a moment. So password security is an authentic thing. We're going to talk about this. Now here's the idea. With the increased use of the internet, credit cards, and so on, they back up all these passwords by challenge responses. Now we've all come across that. That's where you try to pay with your credit card and it goes, you have to answer one of these questions. What's your mother's maiden name? What's your favorite sports team? And so on. So before you even go, if you're going to do stuff online, you have to choose the answers to those things. Those are called challenge response backup password systems. You have a password, and then you have a bunch of backup questions that verify to the internet that you didn't steal the password. Now, there are a bunch of problems with challenge response systems. Some of these look trivial, but they're not. One of the first is remembering the responses. Now, that sounds trivial, but let's say your mother's maiden name, probably you should know. But a lot of times they go, where were you born? Now, let's say you were born in New York City, and the first time through you wrote down New York City. And now you say, where were you born? You put in Manhattan. Throws you out. Oh, I meant New York. New York. Throws you out because it's exact New York City. Now, there are programs that remember all your passwords. You know, like you program something else. So, in your life, you have another program that tells you your answers to other programs. You can buy these. So that's one. A second thing is the type of information in the backup questions is public knowledge, or can basically be guessed by public knowledge. They always ask you what's your mother's maiden name, but if you're well known enough, you can look up online what the person's mother's maiden name was. If you, they ask you what's your favorite sports team, and you know the person's from New York, there's a high probability they're going to say Yankees.
Facebook.
Oh, your Facebook account. Yeah, they do that. So you can steal it. And during the election of 2008, I don't know if you remember this, not that she's the biggest brain trust in the world, but someone hacked into Sarah Palin's personal account. You know, so as somebody did, suddenly there's a stranger in her personal.
What was her password?
It was probably like Grizzly Mom or something like that. Grizzly. Of course, when they got in
Hockey
there,
Mom. Hockey Mom.
No, when they got in there, they probably found out how unintelligent she really is. But that's someone did that. Second, the next two are actually really theoretical things. There are what are called middleman attacks. Now, the middleman attack is, let's say Connie wants to talk to the bank. I get between them. I mean, on the computer. And she sends me her password. I steal her password, but I don't steal it then. I pass it on to the bank. The bank does the backup questions. She answers it. But I've collected the backup questions in the middle. I go then and steal stuff from her account later on. Now, middleman attacks are more dangerous than what you think, because when you send your stuff out, it's encrypted. The middleman doesn't even have to worry about decrypting there. Just has to get that information. Do you follow what I mean? So, middleman attacks are a big thing. Another problem, and this is with all password things on a computer, are what are called repeat or replay attacks. Now, on most of our computer systems, if you make a mistake, they give you more than one try. And then they say, maybe then they close you down. But you can try again. They don't usually change it. Most computers, you know, unless, like at my school, if you miss twice, they ask you to change your password. Like if you misspell your password twice, or they'll say, then they shut the account down and they ask me, can you do it? That's kind of thing. But in many, someone keeps guessing. Let's say they stole your password. Somehow they steal your password. And now they want to get in. What they do is they just keep trying every possible answer to the security question. They can even steal, if they don't shut you down, they even steal your password that way. They put in some program that will go through thousands and thousands of passwords, starting with some basic idea. Because most people do the obvious in choosing their password, some variation of their name. Okay? So, for you, Sal, they might say, Sal Lear, Sal, Sal 1, Sal 2.
Come on, you just gave out my password. You don't want to go to my email, though.
You're going to get rid of all that.
You'll be very surprised. A lot of stuff there, Ben.
Yeah.
Not the right stuff, Ben.
There are a bunch of present solutions to these things. Zero knowledge password pros. There's password systems based on RSA. And this is what a lot of businesses use. They use something called timed out RSA.